Hi Year 12 Maths General students. This lesson's a bit of an overview, just tying up all the topics we've covered across Unit 3. We're essentially going to review using statistical values and observations generated by a regression analysis that we've conducted on bivariate or time series data, and that helps us obviously develop a thorough understanding of the association between our two variables being investigated. Okay, so when we get a particular question that involves a bit more of an in-depth analysis, performing a regression analysis can involve some or all of the following techniques. So to start with, you would identify the explanatory and response variables of the data you're investigating. From there, you would construct a scatter plot or a time series plot to investigate the visual nature of any association present. You then, if required, calculate residuals, and that gives us a little test on the validity of a linear association between the two variables. We can calculate the correlation coefficient, or your R value, to mathematically verify the strength and direction of a relationship. From there, we can go into our least squares regression model or trend line. And we may need to calculate the coefficients, B, which is your slope value, or A, which is your y-intercept, using that least squares regression process, and you may have to interpret those in the context of the data. If you have fluctuations within your raw data, you can demonstrate using techniques such as mean smoothing, or if you see seasonality in there, you can de-seasonalize your data to remove fluctuations. You'd also calculate your coefficient of determination, or R squared value, and that will establish the accuracy of any correlation present and also the predictive power of your association between the explanatory and response variables. You may have to use the regression model you've developed to make predictions, and lastly, you may be asked to write a brief report on your findings. If you are asked to provide a summary report, you should include what was being investigated in terms of your explanatory and response variables, including some sort of classification of the type of numerical data you're dealing with. You should include a mention of how big the sample of data was, any visual comments you're observing from a scatter plot or time series plot, quoting your correlation coefficient. Make a statement of whether there are outliers present. Include the equation of your least squares regression trend line in terms of your response variable is equal to your slope times your explanatory variable plus your y-intercept value. Always give some sort of description of the meeting of your slope and y-intercept in the context of your data. Use your coefficient of determination, talking about the percentage variation in your response variable being explained by the variation in your explanatory variable, which also then supports that percentage correlation of the data points fitting your model equation developed. Lastly, always think about and make some sort of comment on the correlation versus causation of the association you're observing between your explanatory and response variable. Discuss any potential of alternative causal explanations by any other confounding variables you can think of, or point out any coincidental reasoning you can see for the association or correlation you're seeing between the explanatory and response variables. Alrighty, let's move on to three examples for you to try and show off the skills that you've learned so far in Unit 3. Okay, question 1 is a complex familiar question. So you're given the raw data, and it's data on a hardware store that's looking at how much it's spending on advertising compared to how much revenue the store is bringing in from sales. And firstly, part A, you're going to use a range of statistical techniques to analyze any potential association between the two variables. From there, perform a regression analysis using the values you've found in Part A to construct a report on the nature of the potential association between money spent on advertising and the revenue raised from business. In Part C, you're going to use the model you've developed to estimate how much advertising should be spent in order to gain a revenue and sales of $1 million. Have a think about what statistical techniques we've covered so far. Perhaps rewind the video to have a look at that list that we covered in terms of what techniques you can use to analyze a potential association between two variables. So press pause, have a go at doing the question, and we'll come back and compare your answer to my sample response. Let's go. Hey, how did we go? So my analysis results include I identified the explanatory variable as your advertising expenditure, your response variable as revenue from sales. I put together a scatter plot using Excel, and you can see just from looking at the scatter plot without the regression line, we have a positive linear association. It looks pretty strong because all of those data points are close to the regression line of best fit that I've popped in there. When I did a little residual plot, again using Excel, you can see that the residuals are like a random scatter over the center line there. So that verifies the linear association. If there was a pattern within there, it would be a non-linear. From the trend line in Excel, it's given us a coefficient of determination of 0.919, which I can then convert into the correlation coefficient by square rooting that value to get a correlation coefficient of 0.9586. So that helps again support a strong correlation because the value is very close to 1. You can see from the Excel generated scatter plot, when I fit that trend line in, I also got the least squares equation displayed, and that gave me y equals 4.9313x plus the $3,769.30. If I think about the meaning of the slope represents an increase in revenue of $4.93 per $1 increase in advertising expenditure. The y-intercept from the model that would estimate the revenue from sales to be around $3,769 if no money was spent on advertising. Part B asks for a sample report. So this is where I would take all of those statistical values and put them in a summary report. I'd start off by identifying my explanatory variable as expenditure on advertising and my response variable as the revenue from sales. They're both numerical bivariate variables, and there's a period of 15 months worth of data. The scatter plot shows a strong positive linear association, which is supported by a correlation coefficient value of 0.9586. There are no obvious outliers present. The equation of the line of least squares regression gave an initial model relationship of our revenue equals 4.9313 times the advertising expenditure plus $3,769.30. And then I've gone on to include that information on what the slope and y-intercept represent. From there, I've then talked about the coefficient of determination being 0.919, which also supports that 91.9% of the variation we see in the revenue and sales can be explained by the variation in the advertising expenditure, which sees a 91.9% correlation between the plotted data points and the trend line fitted to the model. I've then wrapped it up by saying, although an association or correlation is confirmed and evident, it's not clear whether advertising is solely and directly the cause of the association observed. Other confounding variables could include things like the word of mouth by satisfied customers, position of the business in a prominent well-trafficked area, and other things you could probably pop in there. Further investigation into these factors would need to be undertaken. Lastly, we're using our model to find future predicted values, so we're extrapolating, and we need to find the advertising expenditure required to gain a revenue of $1 million. So if I substitute that $1 million into my model equation, I'm solving for advertising expenditure. So to do that, I just need to remove the 3,769 by minusing it, and then dividing it by the slope that was 4.9313. Would have to spend $202,021.92 on advertising in order to achieve that revenue of $1 million. How did you guys go? Hopefully something very similar to my response. Okay, let's move on to question 2. This looks like a time series question. We've got a length of a plant vine measured at the end of each year over 20 years, and the results are shown in the table below there. You have to firstly use a range of statistical techniques using Excel to help analyze the time series data. B, perform a least squares regression analysis. Include mean smoothing to smooth out any fluctuations, to investigate and report on the long-term trends in the time series data. Then you have to use the developed model to forecast the length of the plant vine when it's 20 years old, 5 years into the future. And it looks like the recorded 20-year length was found to be 485 centimeters. So using what you're doing there is you're commenting on the value you've found using the model and comparing it to the actual value when it was 20 years old. And then lastly, predict the age of the vine when it will exceed a length of 6 meters. Okay, so go ahead and have a go at doing that question, and we'll check in shortly after this to see how you went. Okay, welcome back. How did you go? You can see that I've just pasted over the table I've created in Excel, and I have used 5 mean smoothing. You could, of course, use 3 mean smoothing, 2 mean smoothing, 4 mean smoothing, whatever you deem is appropriate, as long as it's done correctly. I've put across the time series plot with, in blue, the raw data, in orange, the 5 mean smoothed data that's been plotted. I put both regression lines in, and you can visually see that smoothing effect that's happened. In terms of my analysis results, I've got my explanatory variable as the time in years, response variable as your length, because in time series analysis, time is always our explanatory variable. You can see again that strong positive linear association between time and the length of the plant vine. There's presence of irregular fluctuations. I can't see any obvious outliers, and there's no obvious presence of seasonality or cycles over those 15 years. Just concentrating on the raw data for now, my coefficient of determination is 0.991. And if I convert that into my correlation coefficient, I get 0.995, which supports a strong positive linear association. My equation of my initial raw data trend line is y equals 24.121x plus 10.095. The slope represents an increase of length of the plant vine by 24.121 centimeters per year of growth, and the y-intercept represents the length of the plant when the study began at time 0. So when they first started looking at this plant, it was 10.095 centimeters long according to your model. For part B, I'm taking a lead off that start off by talking about the regression analysis is looking at the association of age on the length of a particular tree line. There were 15 lengths measured after each year of growth. Time series plot showed a strong positive linear association supported with your correlation coefficient value of 0.995. There's the presence of irregular fluctuations in the plot and no obvious outliers. We can start by talking about the original equation of the least squares regression line, giving us our initial model, where the length of your plant vine is 24.121 times the age plus 10.095, and what the slope meant and y-intercept. Then I think it's super important that you move on to refining your model using that 5-point mean smoothing, and that gives your refined model of its length being 23.905 times the age of the plant vine plus 10.247. So that means your slope value, then it represents an increase in length of 23.905 centimeters per year, and your y-intercept then changes to, not by much, but it changes to predict the length of the plant being 10.247 centimeters long when the study began. This is a better fit model, and you use the coefficient of determination to show that, because you can see it increases from 0.991 to 0.996, so that means a better 99.6% correlation between your plotted data points and your trend line. So the coefficient of determination also supports the 99.6% of the variation in length of the plant vine can be explained by the variation in the plant vine's age in years. Finally, wrap it up by talking about the other factors that could contribute to the plant vine's growth, which could include your growing environment, water and nutrient supply, exposure to sunlight, and things like the genetics of your plant vine. So even though it's determined there's a strong correlation between the length of the plant vine and time is not the sole cause of length changes because of these other variables. You could go on to say that if one or more of these variables were changed, this would have an effect on your model. Some of those things would stop the plant growing altogether and it may die. Another limitation of the model is thinking about the fact that living things, well, growth is finite, so at some stage the plant will stop growing and die. A bit morbid, but that's the reality, and that makes the model a bit limited in predicting the future length of the plant vine down the track. Okay, the last two parts we had to find the length of the plant when time was 20 years. So essentially just subbing that into your model equation, and we can find that at 20 years you can predict the length to be 488.347 centimeters, which when you compare it to the actual measured length at 20 years, that was 485. So your model's not too bad at predicting future values. Then swapping it round, we've got to find the age when the length is 6 meters. So you convert that first to centimeters, sub it in, minus the 10.247, divide it by the slope of 23.905, and that gives you an age of 24.6753. So essentially, the plant will be in its 25th year of growth when it gets to 6 meters long. Okay, a last question. Question 3 I've put in the form of a complex unfamiliar question. So you're told a company sells toys and records the number of sales in millions of toys over 2 years. And you can see the sales are recorded in quarters. It then goes on to ask, by deseasonalizing the data, develop a least squares regression model to predict what the company's projected sales of toys will be in the second quarter of 2008. Okay, so you can see this question doesn't step you through what to do. You have to be able to recall all of the steps it takes to deseasonalize your data, to come up with your model, and then think about how you can use that model to find the projected sales of toys in the second quarter of 2008. Alright, so press pause and have a go, and we'll check back in shortly. Alrighty guys, how did we go? Again, I used Excel to help me do these calculations fairly quickly. So the first thing I need to do is to find the average sales for each of the years. So I found the average sale for 2005. I then found the average sale for 2006. From there, I then found the seasonal indice for each quarter. So I took the raw sales and divided it by the year average to get the seasonal indice for quarter 1 2005. I've shown the example calculation down there for that one. From there, once I've found all my seasonal indices, I would then check that each year's seasonal indices add to 4, which they do. I then need to go ahead and find my average seasonal indices for each quarter. So the example I used was finding the first quarter seasonal average. So I took the first quarter seasonal indices and I averaged them to get 1.26. Okay, and I did that for the other 3 quarters as well. I also made sure that once I had found all of those indices, I added them up to check that they come to a total of 4. Okay, then the last step is to deseasonalize these figures. So the example calc that I've put here is if I'm deseasonalizing this first raw sales, so quarter 1 2005, I take the raw sales and I divide it by the first quarter seasonal average of 1.26, and that gives me a deseasonalized sales of 43,000. Then going on to deseasonalize the rest of the data. From there, I then took this data and I created a pivot chart plot of years and quarters versus sales, and you can see here that my raw data sales is quite fluctuated, and by deseasonalizing I've smoothed it out. The equation for the line of best fit there of the deseasonalized values is negative 0.9404x plus 42.739, and you can see an R squared value was 0.2863. So putting it in the context of the data, this gives a deseasonalized model equation of sales, millions of toys, is equal to negative 0.9494 times the number of quarters since the start of 2005 plus 42.739. And I just put a little note in there saying that slope showing you that we've got a deseasonalized decrease of 940 sales per 1 quarter, which I mean isn't great news for the company. Answering the question that's asked, we want to know the predicted sales in the second quarter of 2008. So that means if you go and count the quarters from the beginning of 2005 until the second quarter of 2008, that's 14 quarters. Subbing 14 quarters into my model equation, I get a deseasonalized sales of 29.4474. And remember, you need to re-seasonalize that using the second quarter seasonal average of 0.71, so from our table up here. And that gives us a re-seasonalized sales of 20.91, which I've rounded to 21,000 sales predicted for the second quarter of 2008. All right, how did you go? Hopefully you experienced some success or a lot of success with those 3 questions now that you've gone over the content of Unit 3. where hopefully you'll be able to tie together all of these little skills you've learned over the series of lessons we've done. And you can perform a regression analysis using the various techniques and be able to analyze and then interpret the findings between the variables you're investigating. Depending on your assessment item, hopefully that helps you to briefly summarize your findings between the variables you may be investigating. Okay, thank you, Year 12s.